When you think about drilling for oil, what's the first thing that pops into your head? Probably some old-timey image of a big metal tower in a dusty field, right? A pipe just spinning its way into the ground. Well, that picture? It's a little out of date.
So let me just ask you, do you think getting oil is a simple process? Just drill a really deep hole and you're good to go? Because honestly, the reality of how it's done today is way less about brute force than you could ever imagine.
Yeah, it's much closer to something like robotic deep-sea surgery, all guided by AI happening miles under the ocean. So how on earth did we get here? Well, it all starts with the basics.
Okay, before we get to the mind-bending robots and AI, we have to start with the fundamentals. I mean, the basic toolkit for just making a hole in the ground is, on its own, incredibly sophisticated.
And right at the heart of it all is this stuff called drilling fluid, or as everyone in the industry calls it, mud. But let me be clear, this is not the kind of mud you find in your backyard. Think of it more like a liquid Swiss Army knife, a seriously engineered fluid that has to do a bunch of critical jobs all at once.
First off, it's got to cool and lubricate that drill bit, which is just tearing through rock under insane amounts of pressure. Second, it acts like a non-stop conveyor belt, carrying all the ground-up rock, the cuttings, back up to the surface to keep the hole clean. And third, and this one is absolutely vital for safety, the sheer weight of the mud creates pressure that pushes back against the rock formations, stopping oil and gas from rushing up uncontrollably in what's called a blowout.
Now, engineers are always playing a balancing act. You've got water-based muds, which are way better for the environment, but they just don't perform as well when the going gets tough. On the other side, you have oil-based muds. They provide amazing lubrication for really complex and deep wells, but they come with a much bigger environmental risk. It's this constant engineering trade-off between performance and protection.
All right, for decades, drilling was pretty straightforward. You just went straight down. But then, someone had a revolutionary idea. What if you could turn a corner miles underground? That single thought kicked off a technological leap that completely changed the game. Welcome to the horizontal revolution.
See, a traditional vertical well is kind of like poking a single pin through a big sheet of paper. You only touch one tiny little spot in that layer of oil-rich rock, which might only be a few feet thick.
But a horizontal well? It's a whole different story. After drilling straight down for miles, engineers can actually steer the drill bit, turning it 90 degrees to drill sideways, directly through that target layer. So instead of a tiny pinprick, you're creating this massive underground highway that's in contact with the oil for its entire length.
And I'm not talking about a short little jaunt. We're talking thousands, sometimes even tens of thousands of feet that a single horizontal well can travel inside that sweet spot. It just dramatically boosts how much oil you can get from one single well. This amazing ability to steer underground basically threw open the doors to new possibilities. It pushed engineers to design tech for some of the most extreme, most hostile environments you can possibly imagine.
Let's talk about deep water drilling. On the seabed, thousands of feet down, the water pressure alone can be over 3,000 pounds per square inch. To put that in perspective, that's like trying to balance a couple of cars on an area the size of a postage stamp. Every single piece of equipment has to be tough enough to survive that constant, crushing force.
And the master control center for all of this deep-sea action is a piece of gear with a pretty festive name, the Christmas tree. Don't let the name fool you, though. This is no decoration. It's this incredibly complex stack of high-pressure valves and gauges that sits on the pitch-black seafloor, acting as both the main faucet and the ultimate safety switch for the whole well.
Now, back on land, you've got rock formations like shale that are so dense, so tight, that oil is trapped inside and just can't flow out. That's where hydraulic fracturing, or fracking, comes into play. They use super high-pressure fluid to create a whole network of tiny little cracks in the rock. But here's the real magic. They mix in what's called proppant, basically tiny grains of sand or ceramic that rush into those cracks and prop them open, creating permanent little highways for the oil to finally escape.
So, what do you do if the oil is basically as thick and sticky as molasses? Well, in places like Canada's oil sands, engineers get really creative. They drill two horizontal wells, one right on top of the other. They pump high-pressure steam into the top well, almost like a giant underground steam wand. This heats up the super thick oil, called bitumen, making it running enough for good old gravity to pull it down into the lower well, where it can then be pumped to the surface.
So we've conquered extreme environments, and we've developed some seriously complex techniques. But the next big frontier, it isn't miles underground. It's happening in the digital world. The drill floor itself is going autonomous.
And hey, this isn't science fiction that's decades away.
The industry is moving from where we are today, with human operators getting help from computers, to having widespread autonomous capabilities on rigs by 2026. That's practically right around the corner.
And the upsides here are just massive. On one hand, you've got an AI that can look at data streaming from the drill bit and make tiny adjustments in milliseconds, something no human could ever do, optimizing speed 24/7. But more importantly, you have robotic arms doing the heavy, dangerous work. This is the real revolution. It's not just about going faster. It's about fundamentally making one of the world's most dangerous jobs a whole lot safer.
But wait, what about all the oil that gets left behind in old fields? You see, even with all this incredible technology, we still only recover a fraction of the oil in any given reservoir. And that's where the next generation of recovery tech comes into the picture. This table, right here, it basically lays out the entire story of oil extraction. We pretty much covered those first few rows, from the old conventional wells to fracking and those steam methods. But the real wow, what's next moment, that's hiding in those bottom two rows. This is where we go from geology and mechanical engineering to biology and solar power.
I mean, this is the new frontier. Instead of burning natural gas to make steam, some projects are now using these huge fields of mirrors to focus sunlight and do the same job. And get this, in other places, scientists are literally using biology, injecting custom-tailored microbes into old oil fields.
Yes, you heard that right, microbes. The process is called microbial enhanced oil recovery, or MEOR, and it's basically industrial-scale biology. We are deploying microscopic organisms that go down there and produce their own special stuff, like soaps or acids, to break loose oil that's been trapped for millions of years. It's a way to breathe new life into fields we thought were completely finished.
So from super smart mud and autonomous robots all the way to oil-eating microbes, the quest for energy is just this incredible story of nonstop innovation. It really makes you wonder, doesn't it? As technology keeps unlocking resources that we thought were impossible yesterday, what kind of new energy frontiers is it going to open up for all of us tomorrow?